In this simulation, what we're going to do is we're going to take a look at the effect that temperature has on the volume of a gas. So just as we saw in Boyle's law, we have a closed cylinder here with a fixed amount of gas molecules. And so we have a certain number of moles that are trapped within this cylinder. And in order to keep the gas pressure constant, we're going to enable this piston to move freely so that the internal pressure created by the gas equals the constant external pressure. Because remember, we want pressure to be a controlled variable. So let's go ahead and take a look at what effect temperature has on the volume of this gas. So in this setup, we are going to take a look. We're going to increase the temperature of these gas particles, and we're heating them up. And we should notice that the kinetic energy, so the movement of these gas particles, becomes greater. And that means that the kinetic energy increases, which is only affected by temperature. The number of collisions is going to increase, and the forcefulness of those collisions also increases. So we're going to collect some quantitative data. And I'm not sure if you noticed, if I go back and redo this one here, as we are increasing the temperature, notice that the pressure here is remaining constant within the cylinder, but we notice that the volume that those gas particles occupy is also increasing. So we notice that as temperature increases, the volume in which the gas occupies also increases. And again, the reasoning for that has to deal with the kinetic molecular theory. We have an increase in kinetic energy, which is only increased by temperature, because that's what temperature is a measure of. We have an increase in particle collisions, and the forcefulness of those collisions also increases. That causes an increase in internal pressure, which then pushes out on the side of the container. And in order for the pressure to remain constant, that volume has to increase. We can plot these values of volume versus temperature in degrees Celsius, and we notice that we get a straight line. This is a linear relationship. We can see from the values that the gas expands uniformly with temperature. And if we were to extrapolate, that means to extend our line going backwards, we would notice that it intersects the x-axis at a very specific point. So when we are at zero volume, that's at this junction here, what is the temperature at which gas particles occupy zero volume? This temperature should be very significant to you. If we were to convert those temperatures and plot volume versus temperature in Kelvin, and if we did the exact same thing, we would notice it's still a linear relationship. So what that is telling us is that it is a direct relationship. When one variable goes up, the other variable goes up. So when temperature increases, so does volume. So if this is a direct proportional relationship, we can see that if we were to multiply volume and temperature, 20 times 0, 21.8 times 25, 23.7 times 50, we would not get a constant value. But if we took the volume and we divided it by temperature in Kelvin, we notice that we do get a constant relationship. We get a constant value. So we see here that if we take volume divided by temperature in Kelvin, we have a relationship that is direct. And so from that, we can come up with a Charles law formula where V1 divided by T1, because that gives a constant value, is equal to V2 divided by T2. V2 and T2 would be the final volume and temperature, and V1 and T1 are the initial volume and temperature.